What we have in front of us here is what's referred to as a related rates problem. You can tell it's a related rates problem. They'll start giving you rates in the middle of the problem. They're going to ask you things like how fast is something moving. So when they want to know about the speed, the rate that something is changing, you're really looking at what's called a related rates problem. And so this is basically a word problem that uses implicit differentiation. The first move on any one of these that you do is really to try to draw yourself a picture to see if you can kind of understand what it's looking like. So we've got a 25-foot ladder leaning against a wall. So if we've got our wall right here, and then we've got our ladder right there, and then we've got the ground kind of coming across like this. So we've got a wall, we've got the ground, and then we've got the ladder. Once you draw out your picture, it kind of starts giving you a sense of what you're looking at. This is also, while this is a classic ladder sliding down the wall problem, this is also the way a lot of triangle setups work. So whenever I see a triangle setup like this, a right triangle problem, I usually come through and I start labeling it out after I've drawn my picture. And the way I would label it is I know that I need an X piece and I need a dx dt piece. I'm going to need a y piece, and I'm going to need a dy dt piece. And I'm going to need what I call the z piece, and I'm going to need a dz dt piece. So the derivative pieces, the dx dt, the dy dt, the dz dt, those are our rates. That's how something is changing. The x, the y, and the z, those are our flat amounts. So in order to be successful at this ladder problem and a lot of these triangle pictures problems that you get, you want to find out a value for every piece of this except for the one that you're trying to go find. So coming back through and looking at the language of the problem, we've got a 25-foot long ladder. So that is not a rate of change, that is a flat amount. That's the ladder, so that is our z amount right there. It's telling us now that the lower end is moved away from the wall at a rate of 6 feet per second. That is a rate of change, that's a derivative piece. We're talking about how this lower end is moving in that direction. So that is a dx dt piece. So this would be our 6 feet per second. Then they want to know how fast is the height of the top changing. So they're asking us how fast is this piece changing here. So they want to know what does dy dt equal when the lower end of the ladder is 7 feet from the wall. So when this lower end here from there to there, when that distance is a flat amount, notice that's not a rate, when that is 7. So going back and looking at this picture that I drew, I know that I need to be able to fill in for this y value, and I know I need to be able to fill in for that dz dt value if I'm going to be successful at this problem. So going for the y value first, if you look at this, this is a right triangle. So we have 2 out of the 3 sides of a right triangle. So we are going to go back and use our good old friend, the Pythagorean theorem. X squared plus y squared equals z squared. So the x is 7 squared plus y we don't know, that's what we're looking for, equals z squared, which is 25. And now from there, we'll go ahead and start putting all this stuff together. So simplifying this out, we get 49 plus y squared. 25 squared is 625. We're just trying to solve this thing to get y by itself, right? So minus 49, move everything away from that y squared. 625 minus 49 is going to get us 576. And then the last move here, cancel out that squared, you're going to square root both sides of this. So y equals the square root of 576, so that is 24. And so now we know the y value. The last piece of the puzzle that we have to fill in is this dz dt. Remember that this is the amount of change happening in that z direction. And so this is one of those ones that you just kind of have to, they want you to logic your way through what's happening here. Remember that we have a 25-foot long ladder sliding down this wall. As this ladder slides, remember that it's always 25 feet. The ladder is never going to change how long it is. So the amount of change happening in the z direction is 0. So that is just implied in the problem. Very often, if you find yourself needing a rate, especially on a triangle problem like this, ask yourself, is there any change happening in that direction? So here we're seeing that we have no change in the z direction because the ladder is always 25 feet. So that implies dz dt equals 0. So we've plugged in for all the pieces, and now what we need to do is we need to find a way to get dy dt, dx dt, and dz dt to all come together. Well, that is going to come from taking the derivative of your Pythagorean theorem. So this is the relationship. This is how these things are all related, right? Related rates. They're all related through this formula. So to get our dx, dy, dz, dt pieces to pop out of here, what we need to do is we need to go do some implicit differentiation. We're going to wrap this thing in a set of parentheses and we're going to ddt it because everything is talking about time, right, in all of our rates. That's how we know that we're ddt in this equation. So we'll come through this process. Implicit differentiation, whenever I do implicit differentiation, I have a little saying that I keep in my head, and that's every time I take a derivative, I get extra stuff. And what that extra stuff is going to look like is envision there being this little box up on top with that d right there, and we're going to fill that box in with the letter of whatever we took the derivative of over dt. So working our way through this, the derivative of x squared would be 2x. Took the derivative of an x, so I get a dx dt. Fill that box in with an x. Plus, take the derivative of y squared, that would be 2y. Took the derivative of a y, so I get a dy dt. Equals, take the derivative of z squared, that is 2z. Took the derivative of a z, so I get dz dt. Cool. So from here, the beautiful thing about related rates problems that are different than your standard implicit differentiation is at this point in the process, you have everything you need to plug into this equation to solve for your dy dt. So rather than having to do algebra with all these variables, you just start plugging in for everything. So we would get 2, and then x is 7. dx dt is 6. Plus 2, the y we got out was 24. dy dt is still there because that's what we're looking for, equals 2. The z value is 25. And then dz dt was the 0. And so now we just need to clean up the numbers and solve this equation to get dy dt by itself. So we go ahead and start cruising through this thing, working our way left to right. So we end up with 84 plus 2 times 24 is 48 dy dt equals, and then 0 times anything gives us just 0 on this side. And so now we keep moving forward. We'll move the 84 over to the other side. We get 48 dy dt equals negative 84. I'm quickly running out of space here, so I'm just going to move this up to the other side. So we have 48 dy dt equals negative 84. And then go ahead and we're trying to get dy dt by itself, so just divide by 48. Divide by 48, you get dy dt equals negative 84 over 48. And then you can simplify that down. You can pull a 12 out of everybody, so that's going to give us negative 7 over 4. Remember, when you're dealing with a word problem, you always need units on it. We're talking about the change in y over the change in time, so this is going to be feet per second. That's our rate of change right there. And when you look at a problem like this, the positives and the negatives are telling us the direction something is moving. And since our ladder is sliding down this wall, that gap is actually getting smaller. So the negative makes sense because that's telling us that this thing is moving down at 7 over 4 feet per second. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.